All right, so get this. You ready?
I'm ready.
You could become a black hole.
Oh, wow.
Actually, if you were squashed down small enough.
Yeah.
Crazy, right?
That's wow.
Today, we're going deep into the world of black holes
Right.
with the one and only Michael from Vsauce.
Love him.
We've got his YouTube video all queued up.
Okay.
So get ready for a very mind-bending journey to the heart of a black hole.
Black holes are so interesting.
Yeah, they are.
They're regions of space-time where gravity is so strong that nothing, not even light, can escape.
So to kick things off, what actually makes a black hole?
Good question.
Vsauce explains this thing called the Schwarzschild radius.
Okay.
And it's kind of like a magic size limit.
Huh.
Any object squished smaller than its Schwarzschild radius, boom, black hole.
Precisely. Every object has a Schwarzschild radius.
Really?
Take Mount Everest, for instance.
Okay.
If you could somehow compress that massive mountain
Yeah.
into something smaller than a nanometer, you'd have yourself a black hole.
A black hole from Mount Everest. Okay, my mind is blown already.
It's wild.
But how do they actually form out in space? We can't exactly go around squeezing mountains, can we?
Thankfully not.
Uh-huh.
Black holes typically form from the remnants of massive stars.
Okay.
When a star much larger than our sun runs out of fuel,
Right?
it collapses under its own immense gravity.
Wow.
And this collapse creates what we call a singularity, which is a point of essentially infinite density, and that's the heart of a black hole.
So these giant stars, they're like a cosmic recycling program.
Yeah.
Turning into these super dense objects.
Yep.
But if black holes trap light, how do we even know they're out there? Can we see them?
So we can't see a black hole directly because no light escapes.
Right.
That's true. But we can observe their effects on their surroundings.
Huh.
For instance, they cause this phenomenon called gravitational lensing.
Vsauce had some crazy visuals about this. It's like if a black hole is sitting in front of a distant galaxy, the black hole's gravity bends the light from that galaxy.
Yeah.
So we see it all warped and distorted, kind of in a ring shape around the black hole.
That's a great way to put it.
Yeah.
And we can observe gravitational lensing from Earth.
Whoa.
Which is kind of a reminder that these powerful objects are out there shaping the fabric of our universe.
This next part is what I'm really curious about.
Okay.
What if, hypothetically, you were falling into a black hole? What would that be like?
Ooh. All right. Picture this. You're approaching the black hole, and as you get closer, your field of vision starts filling up with darkness.
Oh, wow.
It would be like the darkness is swallowing you whole.
Already getting the chills.
Yeah.
Vsauce mentioned something about a photon sphere, too.
Yes.
Where light can orbit the black hole.
Yeah.
What's that all about?
The photon sphere is a region where the black hole's gravity is so strong that light can actually be bent into a circular path.
Huh?
Theoretically, if you could park yourself at the photon sphere,
Right.
you could see the back of your own head.
Wait a minute.
The light bouncing off the back of your head would travel all the way around the black hole
What?
and come back to your eyes.
Hold up. So it's like a cosmic mirror.
Yeah.
But instead of reflecting your image straight back, it's bending it all the way around the black hole. My brain is, I don't even know.
It's crazy, right?
Yeah.
Time itself behaves differently
Right.
near a black hole. Let's say an observer is watching you fall in from a safe distance.
Okay.
They would see your descent slow down
Really?
as you get closer and closer to the event horizon, the point of no return.
So they see me in slow motion.
Exactly.
Like a movie.
And as you reach the event horizon, the observer would never actually see you cross it. To them, you'd be forever frozen in time at the edge of the black hole.
So I'd be stuck there, like
Yeah.
on the edge of forever.
Kind of, yeah.
What about me? What would I experience as I fall in?
So you wouldn't stop at the event horizon.
Oh.
You'd continue falling towards the singularity.
Okay.
And that's where things start to get messy.
Oh, I have a feeling I know where this is going. This is the spaghettification part, isn't it?
You got it.
Oh, no.
As you approach the singularity,
Right.
the difference in gravity between your head and your feet becomes extreme,
Okay.
and you get stretched out
Oh, yeah.
vertically like a noodle, like spaghetti.
Oh, that sounds incredibly unpleasant. But what happens after you're spaghettified? Like, what's at the end of that journey?
That's where things get really mysterious.
Okay.
Our current understanding of physics actually breaks down at the singularity itself.
Huh.
What happens there is still a big question mark.
Really?
Some theories suggest complete annihilation, while others propose the possibility of being transported to another part of the universe,
Yes.
or even another dimension.
Another dimension. This is getting a little sci-fi for me. But how can we even study what happens there? We can't observe the singularity directly, can we?
It's definitely a challenge, but scientists are very resourceful.
Yeah.
They've come up with ways to study the principles of black holes here on Earth. One way is through something called dumbholes.
Dumbholes. Okay, the name doesn't sound very promising.
I know, right? What are those?
It's like a black hole. But instead of trapping light, it traps sound.
Oh, okay.
An acoustic black hole
Huh.
created in a laboratory. Scientists use special fluids to create a flow
Okay.
that's faster than the speed of sound.
So it's like a mini black hole
Yes,
for sound.
exactly.
That's pretty clever. But how does that help us understand, the real black holes out in space?
Well, they're very useful for studying the fundamental principles that govern black holes,
Right.
like Hawking radiation, a theoretical phenomenon where black holes slowly evaporate over time,
Okay.
can be studied in a more tangible way using dumbholes. Hawking radiation. And that's a whole other topic, maybe for another time. But for now, let's maybe shift gears a little bit
Okay.
and talk about something a little more relatable. Like, where do we even fit into this vast universe full of black holes?
That's a great question.
Yeah.
It leads us to one of the most fundamental concepts in cosmology,
Okay.
which is the cosmological principle.
Right.
And it might surprise you to learn
Okay.
that there is no one single center of the universe.
Wait, what? No center? But that doesn't make sense. Everything has to have a center.
I know it's a natural assumption,
Right.
but the universe doesn't work that way.
Okay.
The cosmological principle tells us that the universe looks roughly the same
Okay.
from any point within it.
Wow.
Imagine dots scattered on the surface of an expanding balloon. As the balloon inflates, all the dots move away from each other,
Right.
but there's no one central dot
Right.
on the surface.
Okay, so like we're all on the expanding balloon surface and moving away from each other.
Exactly.
But if there's no center, where did the Big Bang happen?
So the Big Bang didn't happen at a specific point in space.
Really?
It happened everywhere at once. Space itself was created in the Big Bang, and it's been expanding ever since.
Whoa, okay. So if the Big Bang happened everywhere, does that mean we're all like at the center of the universe in a way?
You could say that. We're all at the center of our own observable universe.
Huh, okay. I'm starting to feel really small right now, thinking about the vastness of it all.
It's certainly humbling, isn't it?
It is, yeah.
And it makes you wonder, if the universe is this vast, what other possibilities are out there?
Oh, yeah.
What other mind-boggling things might we discover in the future?
I think that's a perfect place to pause for now.
Okay.
We've explored some really crazy concepts today, from the formation of black holes to this expanding universe and our place in it.
Yeah.
But don't worry, our deep dive isn't over yet.
More to come.
Stay tuned.
I can't wait.
Welcome back
Back for more.
to our cosmic adventure.
Woo!
Last time, we dove headfirst into black holes.
We did.
And my head's still spinning
I bet.
from all those mind-bending concepts,
Now let's simulate.
from collapsing stars to space-time being warped.
Yeah.
Black holes just challenge our understanding of the universe.
In really cool ways,
Yeah.
like the coolest way.
Before we jump back into the deep end,
Okay.
I want to revisit those dumb holes
Oh, yeah.
we talked about.
Mm-hmm.
It's amazing how scientists can make these mini black holes
Right.
for sound
Mm-hmm.
here on Earth,
Crazy.
but I'm still a little fuzzy
Yeah.
on how those work.
Okay, so remember, a dumbhole traps sound instead of light.
Right.
And scientists do this by using a fluid, often a supercooled liquid,
Mm-hmm.
and creating a flow
Okay.
within that fluid
Yeah.
that's faster
Wow.
than the speed of sound.
The fluid's literally flowing faster than sound can travel through it.
Yes.
Wow.
Yeah.
What happens to the sound waves then?
So think of it like this.
Okay.
Trying to swim upstream against a really strong current,
Yeah.
you get pushed back, right?
Right.
That's kind of what happens to the sound waves in a dumbhole.
Okay.
They try to travel against this super fast flow, but they can't.
Oh, wow.
They get trapped.
So it's not that the sound waves are being sucked in
Right.
by some force. It's that they're just
They just can't overcome it.
overwhelmed by the flow.
Exactly.
Okay, that makes a lot more sense.
Yeah.
But why even go through all this trouble with sound waves?
Well,
What can they tell us
yeah.
about actual black holes?
About the real deal.
Yeah. In space.
Okay, so they're incredibly useful
Okay.
for studying the fundamental principles
Mhm.
that govern black holes.
Okay.
For example, they provide a tangible way to investigate something called Hawking radiation.
Hawking radiation.
Yes.
You mentioned that
I did.
briefly in the last part.
Yeah. It was proposed by Stephen Hawking.
Right.
And essentially, he theorized that black holes aren't completely black.
Really?
Yeah.
I thought they were just like all-consuming and they just grow bigger.
So for most of a black hole's life, that is true. But over incredibly long periods of time, trillions upon trillions of years, they slowly evaporate because of Hawking radiation.
So they kind of fade away.
Eventually, yeah.
Wow. But if Hawking radiation is so faint, how can we even study it?
It's definitely a challenge.
Yeah.
Directly observing Hawking radiation from an actual black hole, very difficult with our technology right now. Yeah. It's like trying to hear a whisper in a hurricane.
Right.
But dumbholes create a controlled environment where scientists can gain valuable insights into how Hawking radiation works.
Okay, that's awesome.
Yeah.
It's like using a magnifying glass.
Right.
To study something tiny.
Exactly.
Far away. But speaking of mind-bending black hole stuff, time dilation.
Yes.
Can you remind me?
Of course.
It
all goes back to Einstein's theory of general relativity.
Right.
Yeah. Essentially, gravity warps space-time, and this warping affects the flow of time. The stronger the gravity, the slower time passes relative to an observer in a weaker gravitational field.
So if I were hanging out near a black hole, time would move slower for me than for someone back on Earth.
Precisely.
Wow. And as you get closer to the black hole, time dilation gets more extreme.
Well, more and more extreme.
Huh? So you could potentially travel into the future?
You could, theoretically.
Whoa. Like I could come back to Earth and it would be centuries later.
Theoretically,
Or millennia. Wow. But this is all...
So hypothetical.
Hypothetical, right.
Yes.
We can't actually experience this.
Not yet, at least.
Right. But it's fascinating to think about.
It really is.
That time is relative.
Absolutely.
It can be warped, stretched. Time is not the same for everyone everywhere.
Yep.
This is making me question everything.
I know, right?
I thought I knew about reality.
It's crazy.
This is why I love science.
You do.
It constantly makes us rethink everything. But with black holes, there's still so much.
So much that we don't know.
Like what?
Well, one of the biggest things is the singularity at the heart of a black hole. Our current laws of physics just break down at that point of infinite density.
Okay.
We just don't have a complete picture.
It's like the ultimate cosmic enigma.
It is.
What else? What other mysteries are we trying to solve?
We don't really know how black holes influence the evolution of galaxies. That's crazy to think about. I know. These objects, they're smaller than our solar system, but they can affect entire galaxies. It's wild.
Yeah, it's like the most extreme things are connected to everything. And then wormholes.
Ah, yes.
Right. Those tunnels through space-time.
Yes.
Are we talking science fiction here?
Okay, so wormholes are still hypothetical.
Okay.
But some theories suggest that rotating black holes could create those conditions for these space-time shortcuts.
So it's not entirely impossible.
Exactly.
That's both exciting and terrifying.
It is.
The universe is just full of surprises.
So many.
Yeah. Black holes just challenge everything we think we know
about reality.
Yeah. And they push the boundaries of science. And there's still so
much to learn.
To discover.
Yeah. I think we've covered a good chunk of the mind-bending aspects.
Of black holes.
Black holes.
My brain needs a little breather.
I bet.
But before we completely escape the pull of this topic, there's one more part.
One more.
To our deep dive.
All right.
We'll be back.
Yes.
To wrap up.
Okay.
And maybe even answer some listener questions.
Ooh, fun.
About black holes.
Okay.
So stay tuned. Welcome back to the final part. Of our black hole odyssey.
It's been quite a ride.
It has.
Through the cosmos.
I'm still reeling.
I bet.
From all the mind-blowing concepts we've explored.
Time dilations.
Spaghettification,
right.
Dumbholes.
Those dumbholes. So crazy.
Here on Earth.
I know. Incredible.
Before we wrap up,
okay,
I'm curious.
Yeah.
We've talked a lot about the theory, but what about actual observations?
Oh, yeah.
Like, have there been any discoveries that have, like, really changed things
Oh, absolutely.
in black hole science?
One of the biggest was the first ever image
Oh, yeah.
of a black hole's shadow
I remember that.
back in 2019.
I was everywhere.
It was huge.
That blurry orange ring.
Ring-like
I
structure.
remember thinking,
Yeah.
that's it.
Right.
That's the mighty black hole.
I understand that. It may not be the most visually stunning,
Right. Yeah.
but it confirmed a lot of our theories.
So we finally, like, put a face to the name.
That's a great way to put it.
Right.
And it wasn't just any telescope.
Oh, yeah.
It was a global effort.
Really?
A network of telescopes.
Wow.
All around the world working together.
To create, like, one giant telescope.
Yeah, exactly.
Yeah.
The Event Horizon Telescope.
A telescope the size of Earth.
Pretty much.
That's amazing.
Yeah.
What's next for them?
They're still observing.
Oh, wow.
Gathering data. Okay.
Refining our understanding.
So more discoveries
Maybe, who knows?
could be coming.
Yeah, in the future.
Speaking of the future,
Okay.
what are some of the big unanswered questions?
Oh, there are so many.
About black holes.
Yeah.
That's still, like,
that we're still working on.
keep scientists up at night.
Okay, well, one of the biggest
Yeah.
is the singularity
Right.
at the heart of a black hole.
Mm-hmm.
Our current understanding of physics
Right.
breaks down
Right.
at that point.
At the singularity.
Infinite density.
So it's like
Mm-hmm.
the singularity holds the key
Yeah,
to understanding the universe.
exactly.
Yeah.
It's a region where gravity is supreme,
Right.
where our current models
Yeah.
just fail.
It's like a cosmic roadblock.
It is. It really is.
I'm sensing a theme here.
What's that?
Black holes are like
Yeah.
these cosmic puzzles pushing us
Yeah.
to think bigger.
To think beyond what we know.
Our current limitations.
Yeah, exactly.
And there are so many other questions.
Like what?
Well, we still don't know exactly how black holes influence galaxy evolution.
Right. We talked about that.
They play a role.
Yeah.
But
But we need to learn more.
exactly.
It's crazy to think
I know.
that these objects that are smaller than our solar system
Yeah.
can affect
I know.
entire galaxies.
It's wild.
And then wormholes,
Oh, wormholes.
right?
Yeah.
Those tunnels through space-time,
Yes.
connecting different parts of the universe.
Or even different universes.
Whoa, okay.
Right.
Is this science or science fiction?
So wormholes are hypothetical, but
Basically.
some theories suggest
Right.
that rotating black holes could create
Yeah.
the conditions for them.
So it's possible.
It's not impossible.
Wow, that's both exciting
I know, right?
and terrifying.
It is.
The universe is full of surprises.
Full of surprises.
Black holes, they challenge everything
Everything.
we thought we knew.
About reality, about physics.
They push the boundaries of science
They do?
and remind us
What's that?
that there's still so much to discover out there.
Yeah.
Well, that's it
That's it.
for our black hole deep dive.
What a journey.
We've gone from the basic principles
The very basics.
to the most mind-boggling mystery.
And everything in between.
We've learned about spaghettification,
Yeah.
time dilation, Hawking radiation,
So much.
and those incredible dumbholes
I know, right?
right here on Earth.
Amazing.
But most importantly,
okay.
black holes remind us
Of what?
to never stop exploring.
Never stop exploring.
The universe is full of possibilities,
It is.
and there's always something new to learn.
Always more to learn.
So keep looking up,
Keep looking up.
keep asking questions,
Asking questions.
and never lose that sense of wonder.
That sense of wonder.
Until next time,
See you then.
keep exploring.